Okay, question 7 now is the last of the exponential and log problems. This one again is an applied question, so we're looking at a potentially real-life problem here. The basic equation is written down here. First bit is telling you that there are 300 orchids when the study started, so you've got to show that A is 0.12. So when the study started, T equals 0, and it's telling you that P equals 300. So we can substitute that into the equation. 300 equals 2,800 A, and it's going to be with T equals 0, e to the 0 all over 1 plus A e to the 0, which means 300 equals 2,800A over 1 plus A. Times increased by 1 plus A, I have 300, 1 plus A equals 2,800A, and then expand out, 300 plus 300A equals 2,800A, and now just that's a fairly straightforward linear equation for A. We end up with 2,500A equals 300, A equals 0.12. Part B then, it's telling you that A equals 0.12, and you've got to predict the number of years before population reaches 1,850. So going back to the original equation, I am going to substitute in what I've been told. So 1,850 equals 2,800 times 0.12 times by e to the 0.2t all over 1 plus 0.12 e to the 0.2t. Okay, it's a slightly messy equation, but there's only one unknown in there, and that being t, so we're just going to again multiply through by 1 plus 0.12 e to the 0.2t. So 1,850, 1 plus 0.12 to 0.2t equals 336 e to the 0.2t. Expanding out the brackets, and then I get 1,850 plus 222 e to the 0.2t, 6 e to the 0.2t. Bring the e's to the 0.2t's across, and I end up with 114 e to the 0.2t equals 1,850. Okay, so now that's just an we can get e to the 0.12 e to the 0.2t equals 1850 over 114, which can simplify down to 925 over 57. And now this is just an equation similar to the ones we've had earlier on. Take lns of both sides. 0.2t equals ln 925 over 57. And from that I can get t equals 13.93 or 14 years. The answer doesn't actually specify whether it wants it rounded to the nearest year or not, but both of those will be acceptable. Okay, part C then. This is using A of 0.12, show that P equals 336 over 0.12 plus e to the minus 0.2t. So substituting back in the original equation here, I'm going to put A equals 0.12 into that, multiply everything out, and I end up with P equals 336 e to the 0.2t over 1 plus 0.12 e to the 0.2t. Okay, at this point it's not necessarily that obvious what you would do, but look at where you're trying to get to, and it looks like we have to divide top and bottom of the fraction by e to the 0.2t. So I have P equals 336 all over 1 over e to the 0.2t plus 0.12, and I can rewrite 1 over e to the 0.2t as e to the minus 0.2t, so P equals 336 all over e to the minus 0.2t plus 0.12. The denominator's back to front, but that's the equation we're trying to show. Finally, part D, hence show that the population cannot exceed 2,800. So as the we're looking at what happens to the population as t becomes very, very large, so it's tending towards infinity. The only term in this equation involving t is e to the minus 0.2t, so e to the minus 0.2t tends towards e to a very big negative number, which means it tends towards 0. And so the population tends towards 336 over 0 plus 0.12. And that means the population tends towards 2,800. As it tends towards, that means it approaches but never reaches or never exceeds 2,800.